there's more of these pens if you want to write. There's a whole bag full of pens there. Okay, 13 seconds. Welcome to the computer security seminar. Today's speaker is Professor Jan Vitek of Purdue. He will speak on JavaScript, a pair of results. Jan.
Hello. Hello. So it's a pleasure to address you guys and all the people outside of this room. This talk will be really two talks. So it's two results, as the title says, that we obtained recently on JavaScript. And it is the first time that I'm giving this talk, so there may be some rough edges. So this is about JavaScript, and the first part of the talk is something we call the eval that men do. And it is an analysis of how one particular feature of the JavaScript language, the eval function, is used in practice in real-world software. So if you don't know JavaScript, JavaScript is a fairly widely used language, and it is an object-oriented language that has this one particular built-in function called eval, which takes a string of text and turns it into executable code and executes it. So let's start. So what did we do to get information about how eval is used? Well, we took the web browser that is inside Safari. This is the Apple web browser, and we instrumented to record all the operation that JavaScript does at runtime when you're browsing the web. And we record those in traces, and then offline we analyze the traces to understand the behavior of programs. So what we did then is we did the following analysis. We took the 100 most popular websites and went to those pages and interacted with the website for a few minutes. This is the first of our data set, which we call interactive. And this gives us a good idea of how a typical interaction with a rich website goes. And then to get a broader coverage, we created a script that automatically goes and loads the 10,000 most used web pages and just loads them and records what happens on page load. And this is what we call the page load data set. And the third data set we have is called random, and this is essentially the same as page load. We take 10,000 websites, we load the page, and we automatically randomly click on a few clickable items, and that generates more JavaScript behavior. So there are two numbers that I want you to get out of this. The first one is, out of 10,000 websites, 91% use JavaScript. So if you're browsing the web, you're using JavaScript, period. Okay? So the other number is 59. Out of the 100 most widely used websites we've encountered, 59% of those use eval. Okay. So the majority of your interactions with the web will use this function called eval. So why should we care about eval? Well, there are two reasons we should care about eval. One is performance, and the other one is security. So security, I'll spend a little bit more time on security, but both are important. So why is performance an issue with eval? Well, eval introduces dynamic behavior in your system. So it affects the compiler optimizations that the JavaScript interpreter can do. So the more eval you'll have, the less predictable your code will be, and the worse, most likely, the performance of your system will be. And in terms of security, well, eval is a way to turn user input into executable code. And that's never a happy story. Okay? All right. So a little bit more details on those on the motivation. So here's some data that we gathered. And basically what we observed is that over time, well, let's see. Let me explain the data first, and then I'll give you what is the conclusion. So this is performance data of Firefox over time, of the Firefox browser. And what we did was we looked at different versions, and we looked at the performance improvement on standardized benchmark suite. So the line on top of the graph is the SunSpider standardized benchmark, and you see that the last dot shows that between Firefox 1.5 and 3.6, there was a 13-fold speed improvement. So Firefox 3.6 is 13 times faster than 1.5 on SunSpider. Now, this is wonderful. This is great progress. Unfortunately, if you look at the other line, the one that's labeled Amazon 9, it shows the behavior of Firefox on one of the Amazon websites, and essentially after version 3 of Firefox there is no more performance improvement. So how do we explain that? Well, we explain that by noticing that the benchmarks are very static, they're very predictable, they're very friendly to the compiler and the virtual machine, whereas the real world code has evals, have dynamic features, and it's much less predictable. So motivating our work, this is one of the motivation for our work. We believe that you have to understand how real program work in order to improve performance. So on the security side, here's typical code you will see in websites. And this code is a piece of JavaScript code that is trying to do the following thing. It's calling eval, and it passes as argument this string concatenated with something else. And what could the programmer's intent be here? Well, imagine that resources is an object, and it has a number of fields, and a number of fields that have a name that starts with the word message underscore. And here, the programmer may want to decide at runtime which of those fields to read. So what the programmer has in mind is a usage like this, where you say eval of a string that look like resource message underscore hello. Sort of read the message underscore hello field of the resource object. And what the programmer probably doesn't want to happen is the following. That the string we concatenate starts with a parenthesis and then has a call to the delete all method, assuming there's such a method, of the files object. So both are possible. It all depends what the value of input is, right? Now, the second is probably going to fail at runtime because it's likely that the resource object doesn't have a method called message underscore. But it will only fail after the delete all has been performed. Okay? Because it's evaluating the arguments, and then it finds out, well, there's no such method, and it will return undefined. So, what did the programmer do? The programmer added a validate call here. And what is validate? Well, most likely it's a little parser that checks that what input you're providing is actually just a sequence of character with no braces, nothing funny going on. Okay? All right. So the danger here is that for every use of eval, you have to create your own little parser. And if you mess up in that parser, you will allow patterns of code that can lead to attacks. So in some sense, eval is much too powerful here. It's like, you know, trying to kill a fly with a shotgun and making sure you're giving bulletproof vests to all the members of your family just to be safe. It just doesn't work. And as a side note, the JavaScript language has a safe way to do the same thing, which is to use this square bracket syntax, which does not use eval, and it just turns, just uses a string to access a field. So we set out to figure out how people actually use eval, right? Because it can cause to slowdown and it can cause to security breaches. So it's a good question to understand what people do in the real world. So the first thing we did was get data on how many times eval is called. So our first data point here is a graph that gives you the number of call sites in JavaScript programs on average over all of our data sets that call eval. And you can see that in the interactive data set, the average, the mean number of eval call sites is around 5, and the maximum is 40. So this is encouraging in the sense that it means that most programs have a few places where they use this unsafe feature, not too many, and potentially we could hope that you know, security, you know, you could actually validate and test all of these and make sure that they're safe. In the wider data set, especially when we turn on the random function, we see that the variability of the number of evals increases, and we found website that had over 400 uses of eval. So what does that mean? Well, it means that all depends on your programming style, and some people are very careless about that. The next thing we wanted to know was how much code are you feeding into eval? And this is really important because for performance, the more code you feed to eval, the more likely is it going to invalidate some of your optimizations. And for security, the more code you feed into eval, the more you have to check at runtime. And you know, the more complex the code, the harder is the checking going to be. So this graph gives you the proportion of the sizes, the distribution of the sizes of evals. And essentially, the way to read this is, if you look at the red line, which is the interactive workload, and if you look at maybe at the point where it says 0.08, if you look at this, you can see that 80% of calls to eval in the interactive workload are smaller than 512 bytes, roughly. So most calls to eval are fairly small, 200 bytes, something like that. But if you go all the way, you can see also that all the way at the end of the graph, you can see that there are calls to eval that take 200 kilobytes of code. So you're really loading large chunks of code. And how likely is it that we can validate that call? In our view, probably very unlikely. So the next thing we did was to try to look at what people put in evals. And we categorized it and we counted the different categories. And this is the graph that is sorted in order of occurrence. So the way to read this graph is the most frequent use of eval is to call a function or a method, rather. So what you'll see is the body of the eval is a call with some arguments. Second most frequent use is what is called JSON. It's a transfer format, a data format for JavaScript. And so JSON is probably the safest kind of eval, because it's really just data. It's just a way to send a piece of data with field names. If you go down the list, there are some that are a little bit more well, stranger. So there's a category for type of. What is type of? Well, it's in the body of the eval, the only thing you're doing is testing the type of an object. And we can't find any reason why you would need to put an eval around that. Another thing that people do is the body of the eval is a single variable, like x, eval x. And again, there is no good reason to do that. You could just write x. You don't have to. And then, you know, it goes on, assignments, declaration, white spaces, and so on. So the most, from security/performance point of view, the most distressing category is the category we call other. And this is for code that is just too complex to simply categorize. And that means it's doing, you know, more stuff. And there's a lot of that, and that means, you know, it's going to be very difficult to analyze systems that use that. So another thing we tried to categorize is, or to look at, was what is the eval doing? So by that we mean, when you're running an eval, are you looking mostly at local data, or are you looking at global data, at shared objects? Are you modifying mostly local data, or, you know, global data? So from a security point of view, if you're working on local data, you're probably not doing anything bad. But if you're reading global data, you may leak secrets. If you're writing to global data, you may cause, you know, integrity violations. So this graph is labeled by these W and R's, which means read and write. And the first bar says 10% of the evals read and write local data. That's the only thing they do. Doesn't show. Aha. Well, I sure didn't. Is it back?
Yeah.
Okay. So the graph shows the 10% of this is perfectly safe and harmless. And then at the other end, 10% is reading and writing global data. I won't bother telling you what the other, and the middle bar says that 60% is writing to local and reading from global. So what that means is, well, if we're worried about, you know, leakage of secrets, that 60% bar is something we have to look at. If we're worried about integrity, the last bar where we're writing to global data is the one that we have to worry about. So again, the message is there is a lot of non-local behavior happening, and we have to worry about this for security reasons. The next bit of data we got was essentially trying to get at where do the strings that people eval come from. And here the thing is, if the eval is a constant in my program, it's hard-coded, then it's probably safe, because that means it doesn't come from the user input. Okay? If it comes from some AJAX calls, that may be unsafe, because it comes from outside, from untrusted sources. So we counted these different occurrences, and what we come up with these categories. And the categories mostly tell us this, that, you know, there are very few AJAX calls. And then the rest are about the same proportion. So the rest is native/DOM. So what does that mean? It means these strings we feed to eval come from either a call to a native function or from a call to a DOM. So what is the DOM? Well, the DOM is your web page. So the eval is grabbing something from the HTML and sending it to eval. And a native, well, it could be anything that is built in the interpreter. Constructed is a string that has been built by concatenation. And finally, constant and static are strings that are constants in your code, and you just feed it to eval. So what is it to get out of this data? Well, the things that we have to be worried about are evals coming from the DOM, because the DOM may contain parts of data that is not trusted, and constructed evals. Statics are probably safe. And so there's a slightly more detailed version of this, which tries to break for every kind of eval, where did it come from? And we can see that, for instance, if we pick JSON, that the majority of JSON objects come from native sources, and yeah. So once you look at this, you get a better feeling for who, which kind of strings are fed coming from. Or let me reformulate. Looking at this, we can see that, for instance, all the JSON calls mostly come from native and DOM, and some are constructed, and that most of the assignment call declarations are either constants or constructed strings. And so this is how far we got with this project. So we have a large database with over 500 strings passed into eval, 200 megabytes of data, and traces for over 10,000 runs of different websites. And now what we're trying to do is, dig further and try to better understand what security vulnerabilities there are. So, and now I'll context switch. Set two results, and they're only partly related. Partly related because eval is a problem for security, and this second part of the talk is going to talk about a new mechanism for access control, which we have implemented in JavaScript, and it handles eval. So here in faint gray is the code of the Myspace worm. So I'll give you a second not to read it, and I will tell you here is the interesting part of that code. So the interesting part of that code is really these two lines. Without that much, it wouldn't have been possible to write the Myspace worm. And what are these two lines doing? Well, it's a little bit of HTML that has in the style component a URL that calls eval. Well, not quite. Actually, it's if you look at the URL, there's really a line break there at the end of the word Java. There's a line break, and then it continues on the second line with the word script. And so what's going on here? Well, Myspace had a validate method on the HTML that was looking for the occurrence of JavaScript. If it found a JavaScript tag in your HTML, it would delete that element. It would strip it. But the parser that it was using saw Java, new line, script. That's not JavaScript. Okay? So the parser failed, but the browser doesn't care about new line. So when it saw Java new line script, it took it as JavaScript and interpreted this as executable code and called the eval. And the eval called the alert. Here it's just, for example, I just have in the expression just says alert ha, but that's the eval executed the worm. So so what's the point here? The point here is that trying to have security based on filtering of text is difficult. And the parser ambiguities caused Myspace to lose. Another bit of Myspace code was, of the Myspace worm code was this. So Myspace was looking for any use of inner HTML. Well, the Myspace worm just broke that in 2 bits, and 2 bits of string, and sent that to eval. So what's the takeaway here? The takeaway is, if you want to do security of JavaScript, you have to be integrated closely in the browser. You know, these attempts to parse and filter are really bound to fail. And I have a bunch of other examples of really nasty code which confuses all attempts at filtering. So filtering is going to be hard. So what you want to do is you want to prevent, you know, this action from occurring, regardless whether it's wrapped in an eval or it's been, you know, so you want to integrate yourself with the web engine. So that's what we did. And well, more specifically, what we were looking at was the security of web pages like this, so CNN.com, which combines 2 elements. There is code that comes from CNN, and then there's third-party code, these ads. So these ads are, you know, HTML elements that are loaded from some ad server. And these ads contain JavaScript, they have behavior, they're doing stuff. You trust CNN to some extent, right? Otherwise you wouldn't be browsing their web page. But you have no relationship, no trust relationship with Indiana University Health, for instance, which has its ad. Or maybe you do. But basically you don't know. You know, these are other people who are sending code that gets executed in the same page as, maybe if this is Google Mail, as your mail, right? There's same page, and there's untrusted code running. And sort of looking at the CNN page, here are the list of sources. You know, these are all the places that we load stuff from. And, you know, you have probably never heard of most of them, and neither should you, right? So the issue now is, how can we guarantee that these ads will not use some of the tricks I've shown to attack the main provider's code and, for instance, leak, you know, secret information about you, or cause you to do something, you know, click on something you didn't want to click, or something like that. So our problem is that we're focusing on is safeguarding, you know, CNN from the ads. That's our challenge. And for this, we started something we call the GS Locker project, because because the internet is a minefield, and we want to protect ourselves. And so the goals of this project are, you know, protection from ads. And we place the constraint on ourselves that we don't want to change the code of the ads. So we have to be able to run, you know, CNN.com. We have to be able to run the ads that it's loading without any changes. But we are happy to hack the browser. So this is a trade-off, right? This is technology that requires you to change the browser, but all of the code out there ought to be can be run intact, same as before. So what is the problem statement? Well, the problem statement is essentially that a web app is composed of multiple sources. There's code coming from CNN, code coming from other sources. And we can think of these sources as our principles, right? CNN is one principle, and the ads are another one. And probably CNN is more trusted than the ads. And the resources in this system are all the shared memories locations. So all of the objects that are created by JavaScript, well, CNN is creating some JavaScript objects, the ads are creating some JavaScript objects, and these two can share, you know, these two can be shared So that's the resource that we want to control the access of. And the question we have to answer is, how can we control access to JavaScript objects in this environment, and what policies do we want to enforce on the ads? So we'll just simplify our life by saying that there are just two principles: the host H and the untrusted code U, which represent all the ads. We're not going to segregate them. Like I said, access to objects, reading fields, writing fields, calling functions is what we want to control. And we propose a mechanism called delimited histories plus revocation as our way to control access to this data. And I'll explain this in a second. And the policies we will enforce will be user-defined. So you can write a predicate, and I'll show you how this works. So the first thing is histories. So what is a history? Well, a history is essentially the sequence of operation performed by some computation. So imagine you see the operation root.msg is assigned nm. And let's say that this is done by the untrusted code at some time point t. Should we allow that operation to proceed? Well, it's very hard to say. You don't have enough context. You could say, well, if root is the global object, maybe by fiat I will decree that no writes to the global object are allowed. But that's probably too restrictive. Let's look back in time, see what happened before. So just before the untrusted code incremented some counter, okay. And just before that, the untrusted code read something about the user from the document. Now we can say, well, now, given this context, what you're doing is you're leaking the user field into that you got from the document to the global object, and this means at a later time you could be able to send this outside and send it to another server, and then thus leak the identity of the user or leak some specific information. So the idea of history-based access control is to say, well, we will look at chunks of computation and use all the information about we have in that chunk, in that history, to decide whether an operation is allowed or not. So basically what we do is this. We let the untrusted code run up to a certain point. We grab a history, and then we look at that history and decide whether the operations in it are valid. So what would be a policy? Said they're user-defined. So this is sort of pseudocode to define a policy. And this would be the send after read or no send after read policy, which says for each operation in the history, if you see a get operation, that is a read, of data that belongs to a different owner. So, for instance, you are untrusted and you're reading from trusted object. Then set the read field to true. And if you see in this case, it's a download event that's essentially something that communicates through the network, and you have read secret, trusted data, then, abort. So that's a simple policy, very sort of simplified, very much simplified from what it would look like for real. So it says, if you've read a secret, you can't communicate over the network, basically. And we say revoke because it turns out that you don't want just to abort the computation, but you want to also undo its effects. So why do we want to undo its effects? Well, look at the previous example. If we just stop the computation after the call to after the assignment, we may have left the system in an inconsistent state. We may have incremented this counter that maybe we shouldn't have. Or we could have, for instance, installed a function in a global space and thus polluted global space with some junk. So what we do is, in our system, is if we find a security violation, we just undo all the memory effects. We sort of roll back in time the computation to before we started the history. Nothing that you have done ever happened. So that's the two mechanisms. So we have histories and we have revocation. And with that, we can build security policies. So there are a number of loose ends that I should mention. So the first is, when do we start recording a history? What are the bounds? How do we deal with operation when you're recording a history that communicate with, say, the file system or something outside of us, of the JavaScript interpreter, and some JavaScript oddity. So the first thing is, how do we bound histories? Well, it's simple. What we say is, every time you start executing code that comes from the untrusted world, you start a history. When you finish executing that piece of code, we'll stop it. And we validate at the end. That means in order to be able to do that, we have to tag every object with its source. So they're tagged with whether they're trusted or untrusted. And if you try to execute, if you're running in trusted code and you try to start an untrusted method, we start a history. When you leave, we stop it. We call the policies. We evaluate whether you've breached security. Either we revoke or you let you go. If you try to perform an external operation in the middle, we support a form of eager validation that looks at the history so far and then that can either abort or let you proceed. And there's some JavaScript specific things. I mentioned eval. Well, eval can be used to get the trusted code to execute a string that comes from the untrusted world. So in order to avoid that, we run eval and we record for every eval we record a history and we evaluate its actions. So we've implemented that within the Safari browser. It's about 5,000 lines of code, changes, over 29 files. The policies are actually expressed in C++, which means they're much uglier than what I've shown. We ran this. We ran our system over 50 websites, half of the 50 most popular websites that use JavaScript, and we tried it out. And we tried out with the empty policy, and all sites work well. Sanity check. Then we tried a policy that prevents updates to existing fields of the global object. So you're allowed to add new fields, because sometimes you need to install functions, but you're not allowed to update existing ones. And the result is 36 of the websites we ran fine. In 8 of the websites, our tool performed like an ad blocker. So essentially the ad died, but the website was okay. 5 websites we had partial results, so the website was kind of working but had little bugs. And in one case, the website completely died. Then we used the send after read policy, and in this case, 42 websites worked perfectly fine. In 7 cases, we were acting as a good ad blocker, and there was one case where the website was partly incapacitated. So performance-wise, this is the overhead of our tool on 3 websites: MSNBC, YouTube, and Gmap, Google Maps. And MSNBC shows 100% slowdown, so we're running twice as slow. And this is somewhat of an outlier. I don't have a good answer for why. More typical costs are like the ones we see on YouTube and Gmaps, which are about 10 to 15% slowdown, which is perfectly acceptable for JavaScript. So I'll conclude by mentioning that this work was mostly done by Gregor Richards and Christian Hammer and Brian Berg, who left us to go to the University of Washington. That's all I had.
Are there any questions? Are there any answers?
Well,
okay, then.
perfect clarity. I love it.
Perfect lecture.